We were discussing analog gate example in the last class, and I had left the problem halfway through. What we had was a source which was producing a triangular waveform with peak to peak value plus 10 volts minus 10 volts and a triangular waveform. The control signal was at a frequency, if this is at 50 hertz, that was at a frequency which is 3 times more, 150 hertz. So, the control signal was of this type going to plus Vc and minus Vs, a square waveform. You are asked to design a proper diode bridge circuit as shown, wherein the source with source impedance of 100 ohm is connected to a load of 1 kilo ohm here. This is the voltage, output voltage. So, how to go about doing this? We have already discussed this scheme as to how it works, etc. When this is plus Vc, this is this signal, let us say V, here we are control signal. This is how it is varying, goes to plus Vc whenever we want the signal connected, and goes to minus Vs whenever we do not want the signal to get connected. Again it goes to plus Vc, minus Vs, so on. Okay. This is going to be minus Vc. What we apply is going to be the other way about. Here it will be minus Vs and there it will be, okay, that is, here it will be minus Vc and there it will be plus Vs, minus Vc plus Vs, like that. So, let us see what the waveform is going to be. If it works properly, then the output waveform is something that is going to be this one, that is going to be coming at this time interval. Nothing should come here. Again this one will come at this time interval, and nothing should come here, and so on. This waveform is going to be there, this is not there, this waveform is going to be, this is not there, this is going to be there, this is not there. That is how it is going to appear with an attenuation factor. What that attenuation factor depends upon how we select RC, etc. Now, we have seen that the current in this is going to be Vs divided by Rs plus, when all the diodes are conducting, the entire thing is going to be replaced by a short circuit, and Vc etc. can be grounded, Vc minus Vc etc. can be grounded. We have seen that the resistance is Rc by 2 parallel 1K. Let us take Rc, let us just arbitrarily take Rc as let us say 1 kilo ohm. So, we have 3 1 kilo ohms coming in parallel across 100 ohms. That means 1K by 3 is the resistance. That means 1000 ohms by 3 is the resistance. So, that is the current that is going to flow through the source, and this is going to be divided equally through the diodes in this direction and this direction, and that will oppose a current of, we have already Vc by Rc here, therefore Vc by 2 Rc here. Okay. So, this is half the current that is flowing through the source is going to flow through the diode, and that should be less than Vc by 2 Rc. This is an important equation for the diodes to remain conducting. This we had discussed in the last class. Vc by 2 Rc is the current that is going to maintain these diodes in conduction in this direction. And for these diodes, this signal current may oppose. These two diodes, it is going to help. So, at any instant of time, we must have Vc by 2 Rc magnitude always greater than Vs by 2 into this value. So, Vs maximum here is given as 10 volts. So, we have to consider the worst case situation. Therefore, Vc should be greater than 2 Rc divided by 2 into 100 plus 1000 by 3. Rc is already chosen as 1 K. So, this is the equation, this into Vs max 10 volts. So, you can see here that this is going to be the value of Vc, the minimum value of Vc that you should have, therefore, is going to be more than 10 volts because of this factor 1000 divided by 100 plus 1000 by 3. So, this is going to be greater than 3000 by 1300 times 10. That is the factor by which Vc should be greater than 10 volts. So, we should take care to see that this is the magnitude of Vc that should be maintained, should be greater than this value, about 3 times this, then that means 30 volts. And if therefore, it all depends upon how you select the value of Rc. If you select the value of Rc lower, then it is going to be lower. If you select the value of Rc higher, ultimately it can be 3 times that in this, if all Rc's are made same as RL, okay? And since RL is fixed, we do not have any other choice. So, in this case, therefore, it is dependent upon the choice of Rc in relation to RL. So, this is the thing. Now, if that is chosen like that, what about Vs? Vs is the one that prevents the diodes from conducting. So, Vs, when you apply, all these diodes are open and Vs appears here, and at that instant of time, if signal source is going to go to plus 10 volts and minus 12 volts, it should still remain reverse biased. So, Vs is very easily calculated as something which should be in magnitude greater than 10 volts, that is all. So, Vs should be greater than 10 volts. So, this is the condition for our design. These are the two conditions. If Rc is chosen as 1 kilo, I would like you to try out by selecting Rc as 0.5 K and get these two limits for the same problem. Select then Rc as 2 K and get these two limits. This limit remains unaltered, it is independent of Rc, but this limits changes depending upon the value of Rc chosen. So, you can see how by selecting now a value which is lower than this and higher than this, the value of Vc is getting altered. So, please do this homework problem, okay, so as to understand how to design this important analog gate. The output in the last problem is going to be therefore equal to effective resistance, that is 1000 by 3 divided by the 100 plus 1000 by 3 times Vs after the design. So, you are going to get this as 1000 divided by 1300. So, it is going to get attenuated to a certain extent, that is the output. It will not come as plus 10 volts minus 10 volts, it will get attenuated, that is all, but it is going to be connected or disconnected depending upon the control signal. So, this problem is an important aspect of analog gate. Now, we will discuss about semiconductor diode and its characteristics with applications. So far in our discussion, we have assumed that the diode is going to be an ideal diode. What it means is, it is going to conduct in one direction and not conduct in the other direction. That means it is a short circuit in one direction and an open circuit in the other direction. We never bothered about the actual diode characteristics that the diode is going to have. We assume that it is close enough to the ideal diode characteristics and analyzed all our previous applications that way. Most of the practical applications, this analysis is good enough, and you do not have to bother that the ideal diode characteristics differs from semiconductor diode characteristic. But in the future application that we are going to consider, I am going to exploit the characteristic for a variety of applications. This characteristic is that of the semiconductor diode characteristics. What it is, we have already learnt. What it is, we will also now just remember that the current I of the diode, this is this semiconductor diode, which is called a PN junction. PN junction, this way. So positive here, it is forward biased for a current I diode and V diode. Okay. This is the permission of current in this direction. So PN junction diode is what we are talking about now. Can we therefore use this characteristic for a variety of applications? This also is very important. We have mentioned that this characteristic is going to be an exponential characteristic, that is I versus V, okay, I diode versus V diode. How will it look like? I mentioned this, ID is equal to IS exponent V by eta Vt minus 1. Eta is between 1 and 2. Vt is 20, let us say 6 millivolts at room temperature. This is also equal to Boltzmann's constant K into absolute value of temperature divided by electronic charge Q, that is equal to 26 millivolts at room temperature of 300° Kelvin. So please remember this, we do not have to bother about it, it is an absolute constant K over Q, it depends upon, and room temperature T. So eta is a constant factor which is between 1 and 2. Okay. So IS exponent V diode divided by eta Vt minus 1. This relationship is followed. This is the only device wherein this mathematical relationship is followed over several decades of variations of current, from microamperes to several hundreds of milliamperes. Without any sort of problem, this relationship is followed faithfully. So this is an important relationship in mathematics also, which can be used for signal processing. The plot looks like, we have seen this. In forward direction, Vd is, let us say, the forward voltage is going to be steeply rising, current is going to steeply rise as voltage goes on increasing. This region is typically of the order of 0.5 to 0.6 for silicon, and thereafter is going to be very low current. This is what is called reverse bias region, and at a certain point maybe it is going to break down at a very large voltage, right, it is going to break down. So, that also we have discussed earlier. This region, it is called a Zener diode. Breakdown may be formed by what is called an avalanche phenomena or Zener phenomena, but these diodes which are used in this region are called Zener diodes. The diode is rectifier diode is primarily used in forward biased and reverse biased region where it does not break down. Earlier we have mentioned that for our rectifier diode, the peak inverse voltage rating should be such that the diode never breaks down. Diode is always in this operating region. So, let us see how this relationship can be understood by us. If I diode is equal to Is exponent this thing, in the forward bias region, when Vd is much greater than eta Vt, this can be approximated. I diode is very nearly equal to Is exponent Vd by eta Vt. This one can be ignored compared to this exponential relation. That is why it increases enormously with current, with voltage. So, since this is of the order of 25 millivolts etc., by the time we have reached the Vd of the order of 500 millivolts, this factor is coming out to be greater than about 20. So, exponent 20 becomes very huge compared to 1, that is in the forward bias. In the reverse bias region, Vd becomes negative. So, exponent of a negative quantity fast goes to 0. So, Id becomes close to Is minus Is because current flows in the opposite direction. This is called reverse saturation current or inverse saturation current. That means, in the inverse mode the current gets saturated to a value of Is. This is an important property of our semiconductor diode, that is in the reverse bias mode current gets saturated very fast to a value called Is, which is the reverse saturation current. Typically this current may be of the order of picoamperes. For most of the let us say small signal diodes, discrete diodes, this may be of the order of picoamperes. Now, you can therefore imagine that this current, if it is of the order of milliamperes, this one can be clearly ignored, and you can also say that for all practical purposes almost no current flows when the diode is reverse biased. When it is forward biased, we have Id equal to Is exponent Vd by eta Vt. You take log therefore exponent Vd by eta Vt equals I diode by Is in the forward bias region. Therefore, if I now take log, natural log, Vd divided by eta Vt is equal to log Id by Is, or Vd voltage across the diode can be expressed in terms of eta Vt log Id. So, it can be used for logarithmic operation. This is an important device whose current and voltage are related by natural log. So, this can be used for log operation. So, this is one of the important application of the diode. Since the diode voltage is logarithmically related to diode current in the forward bias region, please remember this. this property is also used for what is called data compression. Now, therefore, the current can vary by a huge magnitude from microamperes to milliamperes, the voltage only changes by few hundreds of millivolts. So, the data can be compressed. So, this is also used for data compression. The log operation is suitable for data compression. Then after doing data compression and then processing the signal, etc., you would like to bring back the data to original state. That can be done by anti-log operation, which is ID equal to Is exponent Vd by eta Vt. This is nothing but anti-log operation. So, log operation and anti-log operations can be easily performed by this famous element, which is the semiconductor diode. It is one of the most important applications of the diode, semiconductor diode. Next, let us look at this. Vd is equal to eta Vt log Id by Is. So, Vt is nothing but Kt over Q. If I use two identical diodes, then we will have Vd1 equals eta Kt over Q. This is same for both the diodes. Then log Id1 by Is. Identical diode means what? They have identical values of Is, reverse saturation currents. Then the second diode will have Vd2 equals eta Kt by Q log Id2 by Is. So, these two values of Is remain the same because they have identical characteristics. Such a feature is possible in all integrated circuit components. You subject the diodes manufactured to same operating conditions, same sort of temperatures and same process conditions, etc. So, the manufactured diodes have Is perfectly matched. Then if they are operating at two different currents, the voltages will be Vd1 and Vd2. If I now take Vd1 minus Vd2, then you will get this as eta Kt over Q log this minus this, which will be Id1 by Id2 log x minus log y is log x by y. So, log x minus log y, because eta Kt by Q is common, log x divided by y. Is gets cancelled. So, it is only dependent upon the operating current. So, if I operate one diode at 1 milliampere, another diode at 0.1 milliampere, I can have this as a constant eta KTQ divided by log 1 milliampere by 0.1 milliampere log 10. So, this is a nice technique of measuring temperature very accurately, because K over Q is constant, eta is a constant, T if it now starts varying, you can use this as a thermometer, very accurate thermometer to measure temperature. So, in integrated circuits, this method is used for obtaining what is called temperature transducer. You can put this IC containing nothing but two diodes with amplifiers, etc. You can amplify this by a factor of 100 or so, so that the sensitivity is increased. So, this IC is placed on your forehead, it will read the temperature directly. So, this kind of structure can be sort of established by just using two diodes which are biased to operate at two currents. Let us say how the circuit arrangement looks like. So, this diode has a current of let us say 1 milliampere and this has let us say 0.1 milliampere current. Then the voltage across this is V naught, which is this. This is going to be eta kT over Q log 10. It's a nice thermometer for you. And therefore, this diode as a thermometer is quite commonly used in instrumentation applications, etc. And you can see the simple application merely based on the exponential relationship of the semiconductor diode. Now, let us try to understand the principle of the diode temperature transducer by working out an example. Design a diode temperature transducer with diodes operating at 10 milliampere and 0.1 milliampere. Determine its sensitivity factor. So, this illustrates how one can go about designing such temperature transducers or thermometers very easily by using a pair of diodes which are having identical characteristics. This kind of diodes are easily available nowadays because we have matched pairs of transistors available and the transistor base to emitter junction itself is used as a diode. So, let us assume that we have two diodes whose characteristics are taken to be identical. That means they have the same value of IS, reverse saturation current, and both of them are forward biased by means of a voltage V, positive. This is a positive voltage. So, the current in this diode D1 is I1 and current in this is I2. So, what is I1 equal to? I1 is equal to, let us say, V minus VD1, that is the voltage across the diode is VD1 and this is VD2, V minus VD1 divided by R1, that is current I1. Current I2 once again is V minus VD2, that is the voltage across R2, V minus VD2 divided by R2. So, now we are in a position to find out VD1 is going to be equal to, we have from our earlier this thing, eta Vt log current through the corresponding diode I1 divided by Is. Vd2 is going to be therefore similarly eta Vt log I2 by the same value of Is because they are identical. So, Vd1 minus Vd2 is nothing but V naught. This Vd1 minus this Vd2 is this V naught, which can be measured by any differential amplifier. We will see how such things can be designed later. Eta Vt log I1 by Is minus eta Vt log I2 by Is, which is eta Vt log I1 by Is minus log I2 by Is, which is eta Vt log I1 by I2. Is getting cancelled here. So, this is the output voltage. So, this is eta into kT over Q, Vt being kT over Q log of, let us now see what I1 is, V minus Vd1 by R1, that divided by I2, which is V minus Vd2 by R2, which is now therefore going to give us V naught, which is eta kT by Q, which is good, proportional to temperature, into log of R2 by R1, just a ratio of resistors which we can fix depending upon what we want, okay, plus log of V minus Vd1 by V minus Vd2. It is important to remember that if V is chosen to be very high, V is chosen to be very high compared to Vd1. What is the order of Vd1 and Vd2? I have told you earlier that the diode gets forward biased and the order of this forward voltage for silicon diode is typically between 0.5 to 0.7. So, that is called as the cut in voltage V gamma is going to be between 0.5 volts to 0.7 for silicon. Whosoever manufacturer says this is the order of voltage, forward bias voltage of a diode. So, you can see that if I make select the value of V something which is greater than even 10 times that, about 5 to 7 volts. So, let us say V is made equal to 10 volts, then this is 10 minus 0.5, okay, divided by 10 minus some 0.51 or something, which, okay, may be slightly different. That means it is close to, this ratio is close to 1, that means this is close to 0 already, log of 1 which is 0. So, you have this very neatly coming as so that is the output voltage ratio of resistors to eta kT by Q. What is the sensitivity? Delta V naught by delta T is called the sensitivity of this transducer to temperature variation. This is nothing but eta K over Q into log R2 by R1. So, this is an important factor which you can fix depending upon what you want. By selecting R2 by R1 appropriately, you can fix the sensitivity of this as a very good temperature transducer. In this problem, let us see what do we want. We want to fix the current in one diode as, let us say, 10 milliamperes and the other as 0.1 milliamperes. We can ignore this as long as we select this much, greater than 0.5 to 0.7 volts, which is the cut in voltage of the diode. So, we have selected, for example, this as 10 volts. So, if this is 10 volts and I want a current of, let us say, 10 milliamperes flowing in this, if I ignore this, current is 10 volts by R1. So, 10 by R1 is approximately equal to I1, and that is going to be equal to 10 milliamperes, let us say. So, R1 is going to be 1 kilo ohms. Design is over. Next, I2 has to be again fixed. Again 10 minus Vd2, which is negligible compared to 10. So, 10 by R2 is approximately equal to I2, and that is equal to 0.1 milliamperes, which means R2 is equal to 10 by 0.1 K, which is 100 kilo. So, the design is simply over. If I make this R1 equal to 1 K and R2 equal to 100 K. So, this sensitivity delta V naught by delta T is going to be eta K by T log of R2 by R1, which is 100 divided by 1. So, this is eta K by Q. which is nothing but you can write this, rewrite this as eta k t, okay, by q. Eta k by q can be written as eta k t by t into q, which itself is going to be nothing but eta v t by t into log 100. So, V t at room temperature is known to you, 26 millivolts, T 300 degree kelvins, eta is 1 or 2, log 100 is the sensitivity factor. You can evaluate this mathematically as equal to 1 to 2, let us say 1 into 26 millivolts log 100 divided by 300 degree Kelvin. This is the sensitivity factor numerically. Please evaluate this and see for yourself how much it is. So, the problem is neatly solved in terms of a circuit that comprises of a pair of identical diodes with R1 equal to 1 K, R2 equal to 100 K with the sensitivity factor of this much. Let us now focus further our discussion into the forward biased region of a diode. That is why I am expanding that region. This region is the region where it is following the exponential law, where we can make an approximation that I diode is equal to Is exponent eta V, that is V diode by eta V. That one can be ignored. And in return we can rewrite this waveform, this voltage as V diode is equal to eta Vt log I diode. Yes. Either this or this. This we have understood and we have seen some of the application. Let us now further see other uses of this diode. When it is forward bias, we say that the voltage across the diode is eta Vt log Id by Is. But Is, the reverse current or inverse saturation current, we have called this. This is heavily dependent upon temperature. The device people say that it doubles for every 10 degrees rise in temperature, that this Is doubles for every 10 degree rise in temperature. So, if we look at the diode characteristic, therefore, since Is doubles for every 10 degree rise in temperature, we can say that the voltage characteristics now, this it is dependent upon Is into exponent Vd by eta Vt. For the same voltage, I can get higher current. For the same Vd, eta Vt remains constant. Since Is doubles for every 10 degree rise in temperature, for a higher temperature, if I draw the characteristic, it will be almost, it is not seen here, but in the forward characteristic, it might go like this. So, as temperature increases, in this direction, this characteristic moves. So, it is the diode voltage, if the current is maintained constant, let us say current is maintained constant, then the voltage across the diode is going to shift towards the y axis, and this temperature coefficient, this is delta Vd by delta T for silicon diode is equal to is an important thing, minus 2 millivolts per degree centigrade rise in temperature. Minus 2 millivolts, 2 to minus 2 to minus 2.5 millivolts per degree centigrade rise in temperature. This itself therefore can be used for temperature measurement, and this is used again for scientific application, particularly at low temperatures, because this diode cannot be used for very high temperatures anyway, because silicon material itself cannot be used. Therefore, for low temperature measurement, this can be very nicely used, just a diode, because its temperature coefficient is going to remain almost constant, and it is about minus 2 millivolts per degree centigrade. That is the temperature coefficient of a diode which is biased at constant current. So, it is going to shift, characteristic is going to shift this way. Please remember this, this also is used for temperature measurement and control applications. So, IS doubles for every 10 degree centigrade. Because of this, the diode which is biased at a constant current has its forward voltage Vd changing with respect to temperature with a negative temperature coefficient of 2 millivolts per degree centigrade. Now, the cut-in voltage, that is, if I extend this exponential thing like this, it almost is a straight line and it cuts this axis. This voltage is called cut-in voltage. For silicon diode is about 0.5 to 0.7. That means I can assume that diode is almost conducting fully, that it is a short circuit, really not at Vb equal to 0, but at a voltage of about 0.5 to 0.7 volts. Until 0.5 to 0.7 volts is reached, current is not substantial, thereafter current is very high, which means I can make another approximation to a diode saying that up to 0.5 to 0.7 current is almost negligible, and thereafter current is increasing very fast, and therefore it is a short circuit after 0.5 to 0.7 volts is reached. That is the cut-in voltage. These are the important parameters that you should remember for silicon diode, and therefore suppose therefore I say that voltage V of a circuit connected like this with a resistance R in series with the diode, which is forward biasing the diode, is given to you. Let us say voltage V is 5 volts and resistance R is 1 kilo ohm, and I am connecting the diode whose characteristic is like that. Determine the current through the diode. How will you go about doing it? Now, let us follow this very strictly. I say that it is not a semiconductor diode, it is an ideal diode, then I know that whenever it is forward biased Vd is 0. So, then current in the circuit I diode is therefore approximately equal to 5 volts by 1 k, which is approximately equal to, this is approximate equal to 5 milliamperes. This is first order of approximation in a diode circuit which is forward biased. What it says is this diode drop is that of the ideal diode, and therefore it is 0. Then I say that it is a semiconductor diode, then immediately it comes to our mind that it is between 0.5 to 0.7. So, let us assume it as 0.6 volts. So, V gamma is equal to 0.6 volts. So, let us therefore now evaluate the current. So, it is 5 volts minus 0.6 divided by 1 k. This is the diode current, second approximation, which is nothing but 5 minus 0.6 is 4.4 milliamperes. So, this is more accurate than this, but anyway an idea about the current is already got here as 5 milliamperes. This is more accurate in this case because it is coming out as 4.4 milliamperes. I want the current very accurately. So, what do I do now? I know that the diode characteristics follows this. So, ID is equal to IS exponent V diode by Vt. This is known to me. IS, if it is given, I can find out what this is going to be. This is the characteristic given. So, and also we know that V minus V diode, whatever it is, which we have taken here as 0.6, here as 0. it is not exactly 0, it is 0.6, but not exactly 0.6, it depends upon this equation, right. So, this is the actual current V minus V d divided by R, that is the actual current, and V d is nothing but V minus, we know that, let us say you can even put eta V t log I d by I s divided by R. This is a very complex equation. You can see here I d we want to determine, it is V which is known to us, eta may be known to us, V t is known to us, R is known to us, again I d is not known to us, I s may be known to us. So, something to be found out is to be evaluated only if we know this, that is to be found out. Okay. Though this is a complex nonlinear equation which cannot be solved easily. So, how do we really get the exact solution for this? This can be done by what is called as repeated usage of, that is how computer also solves these nonlinear equations. First we put the value of I d as 5 milliamperes, that is this approximation, let us say, or this approximation which is a better approximation 4.4 milliamperes here, and evaluate this as I d. Then use this I d here and again next evaluate it. Okay. So, in successive steps we will be approaching the actual value of I d. So, once again let us see I d is equal to V minus eta V t log this I d value will take this approximation, which is a better approximation 4.4 divided by I s is given to us. So, this whole thing is known exactly and we can find out I d. Now, this value is again used on this side, repeated usage of this, ultimately there will be very little difference between one value and the successive value of I d that evaluate. When the error becomes very small, we can say that the final value of I d is reached. Okay. So, you can see the complex way the solution has to be obtained here, simply because the diode is a nonlinear element. Now, this can be done graphically. We will discuss in the next class how this can be done graphically by what is called, by using this equation only, right, concept of load line. Okay. So, this whole thing which is to be solved by using this nonlinear equation, this can be done graphically there by plotting the characteristic of the diode and this equation, okay, in the same curve, and that line that we draw here corresponding to this equation is called the load line. Where the intercept occurs is the operating point. So, these concepts will become clear, and why we should go for such graphical concept, okay, only becomes clear when you are confronted with a problem wherein nonlinearity exists. This therefore has to be solved by successively assuming some approximate value for the unknown and calculating the unknown, and then repeating this several times until the error becomes very small.